in the Colorado area, scientists and engineers. I've since then done some changes, improved it, and that's what I would be presenting today. One thing I want to make sure, I told Ida about this. You know, we are all traumatized right now. We all can think of COVID-19. We think of financial disasters, uh, uh, protests, and so on. So what I will present is probably a little off the main interest, but it should be a good break to do some look at the interesting developments of wind turbines. So what I will do is first give a kind of an educational introduction to what is or how do these turbines work, and towards the end will I address the question offshore or onshore. Some interesting numbers. As of last year, the end of last year, wind turbines were generating 600, and I'll repeat this, 600 gigawatts of power. That means 600, 1,000 megawatt fossil fuel plants or nuclear power plants, 600 of them. 34% of this capacity has been with the Chinese. 100 gigawatts is in the US. And things are moving so fast, and wind turbines have caught the attention of the utilities so much that by 2030 or 2040, if it goes at this rate, 1/3 of electric power in the world will be from turbines. Now, this may be a big vision, but you'll see a little bit that it's not all that optimistic. It really can happen. So notice that I have two other names on the first slide. Walt Musial is my colleague at NREL. His expertise is offshore wind farms. In fact, I'm using some of his slides. Vahan Gevorkian is also at NREL, National Renewable Energy Lab. He's an electrical engineer. He got his PhD at Yerevan Polytechnic Institute. When I saw him in '92, I realized this guy was a gem. And I organized, when I came back, to invite him for 6 months to come to NREL. He did so well that they wouldn't let him go. They changed his visa. He became a US citizen, and he's now the #1 utility integration person in the entire world. That's how capable this dude is. Maybe one of these days you can invite him. He's not a member of AESA as far as I know, but he could give a follow-on presentation. All right, let's go into the slides. This is an old one, 2007. It's history. In other words, we started with commercially proven land turbines and slowly start moving. And then all these last two, which are deeper, 20, 60 meter in the ocean, were a vision, which has now become a reality. And that's what I'm going to spend focus on. Before I do that, here is a simple introduction to what is a wind turbine like. Notice that it has several parts. The tower, and then there's a nacelle. This is called a nacelle, which contains the rotor, the gearbox, generator, and the new ones have in them power converters and power converters and also transformers. They can fit in there. I'm going to show you a picture which you would be absolutely floor you how big these things can be. Then, of course, there's the hub, as you see, and the three blades. The blades are airfoils. They use lift to turn. They turn in between 30 to 60 RPM, rotations per minute, which has to be increased. That's why you need a gearbox from 50 or 60 RPM to what the utilities want, which means 1500 or 1800 RPM. So that's basically is the essence of the wind turbine, both onshore and offshore. So that's first picture. Now that's the next one, is really another tutorial. Look at the waves here. I'm not going to talk about waves. I bet you're going to ask a question. Keep that in mind. What do waves do when you put these turbines offshore? Wind, power in the wind is the cube of the velocity. This is the line. In other words, when you turn it on, when the rotors turn it on, the V cube takes you up to a point where you have what's known as the design feature of that particular turbine. At that point, the blades change their pitch and make, instead of increasing the speed, they remain constant. So the curve goes all the way to the end, and then if the wind gets too high, it cuts off. So the rated power, in this particular case, it's 6 megawatts. At 6 megawatts, the pitch control comes in, holds things more or less constant until the very high winds, after which it gets cut off. So that's basically the feature of the wind. Cube of the velocity, and also the area of the blades, directly in the area. So you multiply those two and you get your power in watts, kilowatts, or megawatts. So that's kind of the basics. Now this is a slide which shows what's happening in United States. The bar charts are of course annuals, but the line, the curve is cumulative, and it goes almost to 100 gigawatt. That's where we are today in United States, which means a lot of effort is going on. This is both onshore and offshore combined. All right, but we always have visions, okay? And here's wind energy supply in the US could go to 20%. Right now it is close to 8%. If you look at this here, 8 and 9%. By 2030, it probably will be 20%. And who knows, you can think big and say 2050, it will be 35% of the electric demand of the country. That's a vision we have. All right, here is the first 30 megawatt wind farm. There's about 5, I can't see all of it, but there are 5 turbines here. And this was installed in Rhode Island. 27,000 megawatts or 26 gigawatt of power is now being generated, tied to the utility and providing electricity to about 16,000 homes in Rhode Island. It's actually going on now, active. All right, here is where the real interesting story starts, namely the offshore. The onshore is simple and easier to do. Offshore, you've got problems to think through. The simplest is the fixed bottom offshores. All you do is you fix with a monopile right there into the sea surface, or you can use a 4-legged jacket, okay, and those are cost effective. But when you go more like 100 meters into the ocean or further, you go to 60-meter depths. There you cannot use fixed bottom. You have to use floating, and that's where the fun comes. And there are 3 different types of systems to float these turbines. One is called TLP, tension leg platform. I'll show you a very interesting example of that. Huge spar buoys that have tremendous buoyancy, and then the semi-submersible. These buoyant forces keep the heavy, big turbines up and steady, and we'll see how this goes. Now in the next slide, I'm going to show it's the same thing, but now notice the countries that are doing these wind farms. Incidentally, a wind farm is one where you have more than one turbine. On the average, 100 to 150 turbines make up a farm. That's what it's called. UK, Germany, China, Denmark, you can see all of them. And things are going so fast. These came to me 6 months ago, and they're already uh, have been updated, all of them. So that's how fast things are going. There is right now 26,000 megawatts fixed bottom and 82 megawatts installed right now in various countries, and I'll show you where they are. Well, they're right here, actually. Look at the numbers. Germany is very, very strong in it, one of the leading countries in wind farms. Okay. This slide shows the costs where your winds are steady, more or less. They're, they're they have their minimum speeds is, or average speed is 7 meters per second, and they're uh, proper for generating electricity cost effectively. So all countries, all continents have costs, and this shows where some of them are going on. Interestingly enough, look, it says 80% of offshore wind resources are in waters greater than 60 meters or greater. That's where the floating systems come. And this technology will be completely deployed by 4 years from now. In fact, it's already deployed. So it probably will be closer to 2023 to get the targets that we're looking at. Now, this is a US map, the wind resource map, and the colors show you the wind speeds. The darker color is the higher speeds. You want the higher wind speeds, higher steady wind speeds. And you see the shorelines have the dark blue. Here is a dark blue, where the wind speeds are enough to make it cost effective to put wind turbines. The rest is all the rest that you see the colors are the turbines used in various places onshore. Now let's look at offshore. Offshore, the best location is North Oregon, south of North Oregon and Washington State. And even better ones are on the East Coast. These very dark ones show you 10 meters per second or more. And remember, the average has been selected to be 7. Actually, some of the turbines are set at higher speeds because they're steady and they maintain that speed year round. That's how you do your selection. You have to be very careful where you locate your wind farms. Very important. That's the first thing you do, is where is the best. You don't want to go too far in the ocean because it's expensive. You want to stay within the 60-meter depth. 60 meters is like what, 3 times 60, that's 200 feet depth would be the, you would not like to go too much beyond that. All right. One of the most important components of the wind turbine is the blade. These are airfoils. What you see here, in 1980, this blade was really a wing of an airplane that created lift and rotated at speeds 50 to 60 RPM. Since then, oops, let me go back down. Since then, there's been a major development, much more slender, a better designed blades that do two things. One, they're composed of, they're made up of composite materials. I'm not going to, I'll leave the more details for Q&A as to exactly what they use. But look, you have a special tip and a trailing edge, and what it does is it reduces the noise of the turbine. Onshore, people make a big deal. Our great President Trump curses turbines because they make a lot of noise, which is silly. I don't know if you have been near big turbines. You have to come very close to the turbine to even hear the swishing noise. But these blades make it even more quiet. And not only that, they're much lighter. This design is as much as 50% lighter, some say 80% than the blades. And the lighter it is, of course, the more efficient it will be to operate. This shows one of the big mamas. Look at this. This is a 107-meter blade, the new blade for a 12 megawatt turbine. These are incredibly big, and you can imagine immediately the problem is on land. You can't carry these on land. You've got to put it on barges or ships and go to the sea. That's one of the reasons I'm going to mention that again. But that offshore is the direction these big turbines are going. The transportation is very hard on land for those big ones. Okay, this is a kind of a repeat. You have the spar buoy, you have the submersible type, and then the tension leg type. All of these are used as they put these wind turbines at sea. Now, this is very important. You have already seen the oil and gas rigs that float. What they float on is precisely the same thing the wind turbines have, much smaller. It's a very nice in knowledge transfer. You didn't have to do a lot of work on that because that already has been done with oil and gas rigs offshore. Then inside the ocean, of course, you have your turbines. I see the turbines here. They usually carry 66 kV. These are dynamic cables that go to a station here. There's an anchor involved and the floating support. So this is roughly the inside of a wind farm. These wind farms offshore, remember, are as many as 80, 100, 150 of them, okay? And so the electrical connections and the power load and all that is a whole different, a whole science of wind turbine, which has nothing to do with the wind turbines. It's basically an electrical problem that you have to deal with. Now here we are. What is the cost breakdown of floating offshore wind systems? I'm not going to tell you how much they cost. You can put that on your question. We can discuss that. But here is a good breakdown. Notice that the turbine itself is only 24%. 25% is the substructure, the foundation, the floating, all that itself is cost as much and slightly more than the turbine itself. Then there are the other problems. The electrical infrastructure is 18%. Assembly and installation, which is another interesting topic. We'll leave it for the Q&A. How do they erect these things in the ocean is really fun to watch. And it's really a science now. And then a lot of incidentals that make up the cost of a single offshore wind turbine. Okay, now let's look at the bottom of it now. You have to anchor this. The floating part is here, but then you have to anchor it so it won't move away with the waves. And the anchor, look at the anchor here. This is a regular heavy anchor which ships use, and it goes deep into the seabed to hold everything firm. So the top part is synthetic moor line. Here's a polymer used for that. And then the other is chain links with anchors, 3 anchors. Now, all this length is longer than the depth, and I'll show you why that's the case. We're setting up a turbine. This is just a schematic of a wind farm. Here is the wind farm and how you connect all the turbines, bring it to an offshore substation platform. From there, you send it to a 115 kV with a cable onshore and then connect it to the utility. Utilities are very much interested in integrating these turbines into their system. This slide is a little complicated. This is what Vahan Gevorkian created, and he won a prize for it. Controllable grid platform. How do you control intermittent and changeable inputs from renewable energy like wind, solar, and so on, and connect it to the grid? He came up with a system which is classic, and it can be used anywhere for utilities to check against whatever wind farm they have to connect to. This particular one shows 4 wind turbines. You use the solar PV system and 2 battery storage system, because sometimes you have to store your energy. This line here is the utility line. The Excel is a Colorado utility system. The red is the test one, and you combine. What you do is you get the input from all these and then match it against what the utility wants. Bring it to a switch, then connect it to the Excel utility. The lower picture here is our Enrel wind turbine test site. All wind turbines come here for testing. Not the very big ones. The biggest, I think, is 3 megawatts for Enrel. That's all I'm going to say about this, because this is a whole presentation of how you do this. And I would, if you're really interested, you have good electrical engineers, you would love to hear my wonderful friend, Vahan Gevorkian, and he will be glad to oblige. Now, one problem you have, many problems with wind farms. One of them is, how do you space them? Here is a sketch, which is not quite correct, because what you want to do is you want to stagger. There's a special distance you keep between turbines, but then the next set is staggered, and so on. The rule of thumb is that if this is the first turbine, the second turbine should be 6 to 8 rotor diameters away, not to interfere with what this wind turbine is producing. So arranging a wind farm itself is an interesting engineering project to work on. You don't want them too far from each other, because what happens is that you have to spend a lot of money on these high-powered cables going from one turbine to another. So it's a cost-effectiveness study. How close you can bring so they won't interfere, how far you can place that they stop interfering with each other. Interesting problem. The next problem is, or the next issue is, you want these turbines to move a little bit. It's called watch circle. It's a 100-meter diameter circle. So the cables are made loose enough that the turbine can move in a diameter of 180 meters. Almost all offshore wind turbines have this special part, and the mooring lines are made to allow this kind of motion. You don't want to go more than that, but that's about the amount. Okay, then all these turbines send their power to the substation in the ocean, or whatever, sea or ocean, mostly the ocean, okay? Wind farm, they collect the power, they're floating, and then they transfer this onshore, which then connects to the utility. That's roughly the picture you face. All right, next one is operation and maintenance. All of these turbines require operation and maintenance. And here is at sea, you have tugboat that comes, and you have a special ladder that actually mobile, goes all the way up to the nacelle to do anything outside. To do inside, there's a door here. You go inside, and there's a crane takes you up to the top of the nacelle, and you can work on the generator. You can oil. It says it here: sensors, computers, lubrication, electrical, preventive maintenance. All is done uh, on site. But if there's a major repair, then you have to take the whole thing on a tugboat and uh, carry it onshore uh, for work. Hopefully, not much of this is in its category. Incidentally, these turbines are built to operate 20 to 30 years. Keep that in mind, 20 to 30 years. So far, the earliest was in 2012, so we have 8 years on them, and they're performing very well. I mean, there's such an advance on these turbines that maintenance is minimal. Major maintenance is minimal. This is the first floating wind farm. It was done in first floating wind farm was done in Scotland. It used Siemens 6 megawatt Siemens turbines. Just for fun, I wanted to show you that. Okay, this is an important one. This is the goal. All renewable energy technologies should have curves like this. You start very expensive, and you want to go to a place where it can compete. The power generated should compete with coal or natural gas. Otherwise, you're going to have difficulty selling these things. Right now, in fact, we are now already, since 2020, shows about 10 cents a kilowatt. This is 10 cents a kilowatt hour right there. We are really closer to 5 cents a kilowatt hour now. Don't even have to wait to 2022. This curve has moved towards the left. I'll show you in the next slide. I'll give you how do you do this? You have technology improvement, lower risk, maturing supply chain, and increased competition. I want to make a point here on maturing supply chain. The generators that are used in the nacelle, one of them is called permanent magnet synchronous generator, which requires permanent magnets. And the big turbines usually use that. They don't use the induction generator. And guess what? 99% of the permanent magnet comes from where? China. So there is a supply chain situation here. And the competition is very important because we are global. Every wind farm teaches something to another wind farm, teaches something to another firm. So being global in expanding the use of wind turbines is critical, in spite of what you hear from the White House. All right, this is a similar, simpler sketch. When we started near 10-meter depth, it was 17 cents per kilowatt hour. This was 2015. Has been a 70% cost reduction. It says 2025. Actually, this is 2020. The shallow water turbines are already 5 cents a kilowatt hour. The future is the floating ones will reach 6 cents a kilowatt hour. Again, I don't think it's going to be 2030. Probably within 10 years, we'll reach that. But it's important to bring the price down to compete. So far, renewable energy has taken advantage of government subsidies, and that has to be removed. We'll discuss the subsidies separately. For wind, the subsidy is such right now, it's 2.3 cents a kilowatt hour is subsidized by the government. It's called PTC, Production Tax Credit. It will expire next year. After that, Congress will either renew it or say, look, you are mature enough, you don't need it. In fact, I believe these turbines are mature enough, we're not going to need anymore. Wind turbines are not going to need any more subsidies from the government. This is a nice chart because it shows where we started. When I was at NREL, we were right here. We were impressed seeing 100 kilowatt turbine. Man, it was something great to watch. Look where we are now. Offshore turbines can be as high as 15 megawatt single turbine, 240 meters tall, blade lengths, like I showed you in the former picture, as big as 100+ meters. And here is the comparable Airbus 380 picture to show you that these mamas are huge. I mean, really. I can't even believe now that you can have a 10 megawatt. Actually, we have 10 megawatt wind turbines offshore. Fixed bottoms are easy. Remember, floating is where the fun comes. Very brief summary. There are policies that we have to deal with. Then the cost estimates they have to make. This is 60 megawatt hour. This is 6 cents a kilowatt hour. This is the target for the offshore turbines. But the big thing here is the lower one here. Significant challenges remain with grid integration. That's a big, interesting problem. Resource characterization. Where are the winds? Where do you put them in the ocean that it's accessible and the winds are relatively steady? New technology development for unique environmental conditions like water, ice, hurricanes. Now, don't ask me, what do you do in hurricanes for the wind turbines? If you notice the map, there will be no wind farms outside on the coastline of, guess what, Florida. No turbine can stand the strength of a hurricane. That's why you go northeast, where environmental conditions are a lot more benign. I don't know how many of you have seen this movie called, let's see, what was the name? It's The Perfect Storm. I don't remember The Perfect Storm. It's an incredible movie. When that happens, you lose your turbines, but that is a 1 in a 500 years system, I hope. So that's why you have to select a place where you do not have very high winds that can destroy the turbines. Okay, now let's go to the meat of it, a few short slides. What are the advantages of offshore wind? Windmills can be built that are larger and taller, and transportation is easier. They tend to be far out at sea, thus they're less intrusive as far as borderlines is concerned, because many countries, many onshore turbines are very close to the boundaries between two countries, and that can create problems. The wind may be so good there that you want to put it out there. But in the ocean, you don't have that problem because you don't go beyond 100 meters. Or a mile, I think, the furthest out. Typically out at sea, there is much higher wind speed and force. The average is 7.5 meters per second. Because there are no obstacles, there is a steady wind in the ocean, which you don't get onshore. Wind farms have a relatively negative impact on the environment. Okay, so that's why taking it out sea, that minimizes that, but it creates its own problem. There are no physical restrictions such as hills or buildings, and so you have the steady winds blowing. Okay, the impact that they may have is, let me go to the next slide, you see that. In the disadvantages, the biggest disadvantage of an offshore wind farm is the cost. They're more expensive than onshore. Okay, so that's why the competition has to bring the price down. The effect of offshore wind farms on marine life is not well understood. I'm sure that will be one of the questions. How about the marine life? What do they do? That is not tested enough. So that's one big question there, to see how marine life is affected by offshore farms. Very tall wind turbines that are 100 meters to 200 meters, have a very interesting new problem in atmospherics. Above 100 meters, especially with the blade being another 100 meters, which gives 200 meters, your atmospheric conditions move from microscale to mesoscale. And microscale winds are different than mesoscale winds. And so you have an additional problem analyzing your wind flow to design and place your turbines. If there's too much difference, then that's one of the conditions that you have to stay away from. Now, to me, the funnest part is, you know, wind is bad enough to describe, it has its own mind. It blows sometimes, it doesn't blow other times. On ocean surfaces, it's a little more predictable. But now you have an aero, hydro, servo, elastic system problem to work together. In other words, you cannot isolate your wind predictions from the hydro behavior, water behavior, the elastic systems. The blades are very elastic, the turbine blades, and so all of those influence each other. So far, there is no good model that combines all of this. So this will be for any new person who wants to go into aerodynamics or hydrodynamics or wind turbines. This will give him a tremendous opening to spend the rest of his life working on this system. Okay, now let's go to the onshore farms. Cost of onshore wind farms are relatively cheap, so that's an advantage. The shorter distance between the windmills on onshore are a little shorter than they are in the ocean because of the waves and the effect of one turbine or another. And so if they're closer, there's less voltage drop from one turbine to another. Wind turbines are very quick to install. Okay, let me make a point here, and then we'll discuss this in a Q&A. You can install these in just a morning, just a half a day. They say these are turnkey. Remember, imagine these wind turbines are now turnkey operations. They're so well arranged that you can really assemble them quickly. And it's easier on land than it is when it comes to oceans. What are the disadvantages? Onshore wind farms are perceived as eyesores. To me, they're beautiful. I love to watch these things turn. But a lot of people think, hey, that's look at your utility towers. Those are the eyesores, not the wind turbines, but it is a problem. They don't produce energy year-round because of blockages. You always have blockages wherever you put them, unlike offshore. Wind turbines create noise, causing noise pollution, and communities complain. All right, that's a problem. That's a disadvantage. All right, so that's where I'm going to stop and give you just a quick look at who are these manufacturers. This big turbine the biggest is Siemens Gamesa. Siemens is German, Gamesa is Spanish, and they combined. They're now partners. They're the largest turbine manufacturers of the world. Vestas, Danish turbines, are number 2, okay? And in fact, if you have been in Yerevan to the Pushkin Pass, we have 3 of these Vestas turbines. They're small, 150 kilowatts, but they're Vestas. They're very reliable. Danes have they've really put a lot of effort in it. For United States, it's GE, Renewable Energy System, and then there are a bunch of others. Notice 2 are Chinese, Xinjiang Goldwind and Sinovel Wind. These are Chinese. And India has 1. Vestas also has decided to go with Japan in addition, using the MHI, which is the word for that is the heavy industries. Mitsubishi, it's Mitsubishi Heavy Industries. Finally, just to show you where the wind farms are now, The biggest one is Walney. It produces 659 megawatts. It has 47 Siemens Gamesa turbines and 40 MHI Vestas turbines. And then it goes down. Look, they're pretty close. So these are the top 9 or 10 that I could find in terms of now operating since 2012, operating wind farms, uh, offshore wind farms. Now comes the final and big, oh my God, look at it. This is the nacelle of the 6 megawatt Siemens Gamesa turbine. Look at the size of it. And installing this is a lot of fun. These are the hub, this is where you put the turbines. There are no, everything is pre-designed. You have actually brackets that the blades, these are where the blades actually get into it and locked. Okay, so you don't have to use nuts and bolts. Here's the company, the workers of Siemens Gamesa. So that's all I have. Official presentation. Now I'm sure we will have a number of questions that we have collected, and let's look at them. Some of them have to do with cost. How are they assembled? What are the blades made of? What are waves doing? How do you dispose of them? And anyway, I'll let Aida to, have you collected some?
Yes, I have collected some. Thank you, Dr. Touryan, for a wonderful presentation. I'm sure we all enjoyed it. So just to remind our participants, you can still type your questions into the chat box. So it should be on the right-hand side of your screen. If you don't see it, just click on the little chat icon at the bottom of your screen, and you should be able to type your questions. In the meantime, actually, I have a question. So you mentioned waves a few times. You promised that you would talk to us a little bit more about what the waves are doing. Can you expand on that?
That's a good question. In fact, the best experience on waves, the Chinese have had it, and they claim that up to 5 to 6 foot waves do not bother the turbines at all. So at least we have a one point there that says that waves have minimal impact if they are properly anchored and properly floating. Yeah, 5 and 6 feet waves are that. That's a pretty heavy storm, and they seem to be okay.
So it seems like having this would be a thing to consider for offshore turbines.
Yeah.
It's not a problem. Okay.
No, well, it's really not a problem. You know, you would think it would, but it seems like there's enough experience, at least from the Chinese side, where they get more storms than we do in our Northeast, that they're not a problem. Yeah.
Okay. And could you please explain a little bit more about how you erect these turbines in the ocean?
That is a lot of fun. I suggest, okay, there are two ways you do it. One, you assemble it, if it's 3 megawatt or 4 megawatt or less, you assemble the whole system on shore at a port, and a tugboat comes and and literally moves it to its site, and then it's already ready. The big the what you call the I keep forgetting to call the name. It's it's the pile, that big heavy pile that this is. These are the near shore ones. The base is already there, and the whole thing goes, and actually the whole thing is ready, and just they fix it to the base, and that's it. For for real floating systems, there are special ships that take the parts with the ship, and then they go. There is a the Chinese have built a sea installer. It's a 130 meter by 30 meter platform. Above that is whose four legs go 45 meters into the down into the ocean, into the sand. It's a stable platform. It's above the waves, and they put all the pieces there and erect them. The first thing you do is the tower. The tower comes in three sections. Okay, you put the towers first, then two gigantic cranes lift the nacelle, which is you show the picture of the nacelle, and put it on the tower. And the last thing to go is to be put on is the three blades with the two cranes attached to the hub. And guess what? I couldn't believe when I heard this. They can do this in 24 hours, including at night. It's basically, I mean, it's so much fun. It must be, as they say, it's a turnkey operation. It's what it is, a turnkey operation. Now, one interesting point comes up. How about if there are winds? How can you erect them? Well, guess what? These big floating turbines with the big Chinese table where they put it, the towers, you can put the towers when there are 10 meter per second winds. You still can assemble the towers. For the blades, you need, the wind should not be more than 7 meters per second. So under windy condition, you still can assemble it, which also to me was a surprise. If you're really interested, I want to suggest you Google, go to the YouTube or Google someplace, and there look at, write down installation of large turbines offshore, and Siemens has very nice 5-minute videos. They show how the whole thing is done. It is really fun to watch. They won't tell you everything because some of it is proprietary, but it's enough to give you a sense of the size of the operation, the number of people involved, and it's how quickly they can assemble this. One each day, even the bigger ones. So that is to me, it was a revelation because I was so used to so much more, 1 to 3 megawatt turbines, not the, as I call the big mamas.
Very true. Well, thank you very much. I'll certainly look at the video. I think that'll be helpful.
Yeah, and if you want to know more about the blades, what you should do is look again. You can go into the internet. There is a company called TPI. T as in Tom, P as in Paul, I as international, and they are the ones that cast those huge blades, which are really made up of composite material. And the novelty is they use carbon fiber reinforced epoxy. There is a lot of epoxy in those blades, and it's quite a science just to build the blade. And it is fun to watch how they do that. Again, it takes a lot of time to show him, but just if you're interested, just Google it and look at it and enjoy it.
Very well. Dr. Touryan, some of our participants are asking for your email. Would you mind clicking back to your first slide?
Yeah, sure, I'd do that. Okay.
So those who have questions can.
Yeah, it is Kenell is my first name. Let me go back to this first slide. Here we go. Okay, here.
Okay.
Kenell.
So
in Armenia, I am called Gnel, Gnel. I did 1 N 2 L because people call me Kennel. They call me on the phone, people who don't know me. Say, is Kennel there? I say, sorry, there are no dogs here in a kennel. And that's a great way for me to know if this is a friend calling me or is one of those people who keep bothering you. Kenell@comcast.net. And the person, as I said, who is really expert in utility integration is Vahan Gevorkyan.
Okay. So another question from our participants is, do you think wind turbines have more potential in Armenia or solar panels?
Good question. The best place to put wind turbines in Armenia are the passes. And Pushkin Pass is one that we have it. There are several passes you can. The problem is if you want to bring big turbines, it is really difficult to get it to Armenia. You have to, the turbine I brought in, which was only 150 kilowatt Japanese turbine, it had to land in Georgia, take it by a train, and the train had to bring it to Armenia. Bigger ones, the Vestas ones that are there now, they had to use a helicopter. They were gifts from Iran, so they had to actually use a helicopter to lift the blades and bring it to Pushkin Pass. So we have winds, we have good winds, but we have problems getting things there. But solar is much easier. You know, it's modular, and you can set it up. And sun is of course abundant in Armenia. So we see more solar photovoltaic and solar thermal than wind turbines. That's my guess.
Okay. Thank you for your answer. Moving on, is it possible to control the speed of the rotor or even stop it when the wind speed is dangerously high, such as during
Oh,
a
yes.
hurricane?
Yeah,
To
the blades do it. They're the pitch control. They first bring it up to its designed power, 6 megawatts, 7 megawatts, whatever it is. Then they then they uh, there's a pitch control, which then keeps the wind constant at that speed, which say is 7.5 meters per second. When it reaches a dangerous point, the pitch, I mean the blades feather, they unlock, they feather, and they just do not produce any power. Yeah, these are very important points to keep in mind, that you have a limited uh, limited span from 7 meters per second to 25 meters per second, I think is the highest. Above that, you don't want to let those blades rotate. Yeah, control is very important.
Okay, thank you very much. And you mentioned that the life expectancy of these turbines is 20 to 30 years. Does
Mhm.
their efficiency drop as they age?
No, you know, they're maintained, they're lubricated properly, they're taken care of if there is any big problem. It looks like, well, we haven't been 20 years yet, so I can't be 100% sure, but they guarantee, in fact, see, utilities pay for these, for the electricity they generate. People ask, where do the costs come? Where you have venture capitals, but that's only 20%. Venture capitalists put money in wind turbines now. That's only 20%. The government subsidizes some, and the rest is utilities are. There's a government rule, government thing called FERC, FERC, uh, which is, I think, what it means is uh, Federal Energy Regulation rule, that utilities should honor working with wind farms, connecting to it, and using the utility for a price that they agree on. That provides, of course, income to these turbines. Right now, there is a 2.3 cent per kilowatt hour, uh, what's known as uh, production test uh, monies that the government gives, but that will transpire in a year. Next year, there will be no more subsidies for wind turbines because they really are mature enough to support themselves.
Right. And you mentioned we need to bring the cost down
Yeah,
to actually make them effective.
right.
Um,
It's even better. Yeah.
okay, well, going off of that, what I found interesting was that the price of the turbine itself is only 25% of
Hmm.
the total cost. You had a very nice chart there at one point,
Yeah.
and
Hmm.
like the structure and the foundation was the other 25%.
Hmm.
50% was divided into other things. And you mentioned that we've learned a lot from oil and gas rigs and the installation to learn how
Hmm.
to set up these wind turbines.
Yeah,
Do
in
you
anchoring, floating, those are the lessons learned from the gas and oil rigs. Yeah. Hmm.
Are there any other areas that we can learn from other systems to perhaps drive the costs down further?
Well, if you look at that list, there are a number of things. Automated more, find, in other words, another thing to do it is big turbine blades should be manufactured at ports, near port sites, so you don't have to have transportation problems. There's also some very interesting, if you want to say big turbine transportation, it's fun to watch how trucks carry these 100-meter turbines. It is incredible how they go and turn curves with 100-meter blade at the back of it. So you want to minimize all that. All that can be done by bringing things closer to the port, automating it more. There's a number of things that uh, advantages, making the blades cheaper and so on. Yeah, there are cost reductions. Maybe using our own permanent magnet synchronous generators instead of relying China for their magnets.
How far away are we from being able to do that? Is that possible for the US?
I don't know. Your guess is as good as mine. But there's enough variables in that circle that I showed you. There are enough variables. Let me see if I can go there. There is enough variables to play with.
Mhm.
Uh, there's always a contingency for it. Construction finance, if you can get good finance, the prices go down. Nobody asks about decommissioning. When they're finished, what do you do with these turbines? You know,
What do you do with them?
90% of a turbine is reusable or recyclable. The big problem is the blades. What do you do with the blades? Because they're composites. You have to chop it to pieces, and there is not a single factory where you can take 100-meter blade and chop it. So so what I think is we have 10 more years to think about it, what to do with it. Okay.
Until
Uh,
they're 30 years old.
yeah. Yeah.
Okay.
And the cost roughly of these turbines is $1 million to $2 million per megawatt for megawatt. I mean, they're not cheap. They're expensive, but they're well funded. They're competitive. They're soon they will return on money on investment. We are there now, or close to. Yeah.
Thank you. And could you comment on the cost comparison between solar and wind power per kilowatt hour?
It should be about the same. For photovoltaic power generation is now almost 1 cent a kilowatt hour. It started at 40 cents a kilowatt hour when NASA started it. It's down to 1 or 2 cents a kilowatt hour. They've really improved on it. But the problem with solar is uh, you have to have storage because at night you can't use solar, whereas the wind blows all the time, especially in the evenings. Uh, so I'm told that a 5 cent a kilowatt hour wind turbine is competitive with fossil fuel, competitive with uh, solar cells, and so on. And I think that's about right.
Okay. Well, I'm going to make this final call for all of the participants to please submit your questions if you have any. And during this time, like to ask you, Dr. Touryan, if you have any final comments to make.
No, in Russian they say "Спасибо большое за ваше внимание." Thank you very much for listening to me. And I don't speak Russian very well, but I know that because after every presentation, the Russian speaker says "Спасибо за ваше внимание."
Mm.
And thank you very much for moderating, Aida. I appreciate it very much.
Thank you very much for accepting our invitation. It was very eye-opening and educational, informational lecture. We
Good.
very much enjoyed hearing your talk.
Thank you, and I appreciate making
Yes.
it's fun for me to present it.
Yes. Thank you so much. And to our participants, if you have any questions, Dr. Touryan graciously provided us his email. So if you think of something later, you can email him.
Don't send Facebook. I hate Facebooks. Send an email. Okay?
Send an email.
Yeah.
Well, again, thank you very much. And thank you to our participants as well.
Okay. Thank you. And many blessings. And stay ahead of the COVID-19.